this one.
Oh. Minus the tension. Equal to 5A.
Okay, and the other one?
FT minus W3 equals M3A.
All right. Yes, there are shortcuts, but process. All right, if we add them together, the tensions cancel out. I'm left with the weight of 5 minus the weight of 3 is equal to M5 plus M3A. So we get M5G minus M3G divided by M5 plus M3 is equal to A. Put it on Earth 2, and so we end up with 50 minus 30 divided by 8, which is 20 divided by 8. So 2.5 meters per second squared. Standard, straight up application of Newton's laws. Let's bring it in. We're going to drop off some of our ideal situation here. We're going to assume that the pulley still has no friction at the axis, so we're not losing anything here, but the pulley is turning now. So let's give it some information here. Let's give it a mass of 0.5 kilograms and a radius of 0.7 meters. We will assume it is a disk. K or C?
I thought it was a K.
I would think so too, but I saw something similar to this with a C, and I thought, wait a second, that doesn't seem right.
I think C is for like an informational disk.
That's what I was thinking.
Okay.
More compact disk.
Okay. All right. So disk with a K, which is my gut there. But
I think that discus is like where it comes from. That's it doesn't matter actually. How do we think about it?
all right. So there is friction now, so it's less than ideal.
The C is or the K is the American English spelling and is often used universally in computer stuff.
Okay. And the C, British.
Yeah.
When are they going to learn to spell?
Sometimes.
The word is eggplant, not aubergine. Anyway. So we have this thing spinning now. This is going to rotate in that direction. The tension is no longer the same because I have friction now acting between the rope and the pulley, and that changes the tensions on both ends of the rope. We still have the same two equations as we had before, with the exception of we are now dealing with subscripts. So T sub 5, T sub 5, I guess. FT3. I am still assuming that the rope is massless and I don't have to worry about the weight of the rope, and that the tension everywhere along here is the same, and everywhere along here is the same, just different from one side to the other. So we've eliminated one aspect of idealism. So my equations become F5 minus FT5 is equal to M5A, and FT3 minus W3 is equal to M3A. I do have an additional unknown now, so I need an additional equation, and so of course, we're gonna bring in our torque equation. The torque, ultimately, I know the net torque is going to be positive K hat, which I've now erased, so let's establish that again. So K hat's coming out. So this is gonna produce positive torque, that's gonna produce negative torque. Well, torque, R cross F. There's my axis of rotation. R is that vector right there. My tension is perpendicular to that radial vector. So I end up with R, I'll just leave it as R. R times FT5 minus R times FT3 equals I alpha. Questions about where this equation comes from? Okay. What's the relationship between V and omega? Between linear and angular speed?
Omega R.
What's the relationship between linear acceleration and angular acceleration?
Omega.
No, omega's not popping in now. This next one.
Is that the V squared over R?
Angular acceleration deals with the fact that as it spins, it's speeding up. The V squared over R or omega squared R is the centripetal acceleration that's pointing towards the center. I'm concerned about it speeding up, not what forces are trying to tear that thing apart. If I take the derivative of this, derivative of linear speed is linear acceleration. R is constant here. Derivative of omega with respect to time.
It's just R.
So d omega over it.
All right, so dv dt is equal to A, take the transliteration, d omega dt
Alpha.
R is constant, R is the distance from where the force is applied to the center. So we have this relationship here. We now have a way of connecting these two equations, this alpha and those A's. We are assuming sort of a perfect friction in the fact that the rope is not slipping. So I now have M5G minus FT5 is equal to M5A. I have FT3 minus M3G equals M3A, just doing substitution there. And then R FT5 minus R FT3 is equal to, well, I is a disk rotating about its center, 1/2 mr squared, times alpha, which is A over R. Looks like I changed up my R's here, so I should settle upon one of them. This last equation can simplify. I know that that R will cancel out with one of those. Every term has an R in it, so this equation becomes FT5 minus FT3 equals 1/2 MA. I guess, M, I just labeled it as an M, in disk. Maybe D in there. So if I now add up these three equations here, add up the left sides, add up the right sides, well, my tensions all cancel out, which is pretty darn convenient. So I'm left with M5G minus M3G is equal to, well, M5A plus M3A plus 1/2 MDA, which is the acceleration times M5 plus M3 plus 1/2 MD. This is the part that gets added, bringing in this little aspect of reality. Before, it wasn't turning, there was nothing going into it, and so we just had M5 plus M3. Now, we have to take into account the pulleys turning. And so we end up with, I guess that's still 20, divided by, that's 5 plus 3 plus 1/2 of 0.5. So 8.25. And we end up with an acceleration of
2.42. 42 repeating. K hat.
Actually, it wouldn't be
Meters
K
per
hat.
second squared.
There we go, that's what I'm looking for. This is linear acceleration. It is less than what we had when the pulley was not turning, which tells us we did something right. Questions here? I want to make reference to the Rube-Goldberg test. There should be one of the tests under old tests for test 3 called the Rube-Goldberg test. Are you familiar with Rube-Goldberg?
Yeah.
One of you is, and the other two are
Sounds familiar.
a complicated set of events to do some simple task. Have you seen the OKCo video, Let It Go? It's a giant Rube Goldberg device there.
Yeah. I've seen like the Goldberg machines.
Okay.
Yeah.
All right. The Rube Goldberg test basically starts out with, I've got two discs attached to each other, and one of the discs has a bar sticking out at the end of it. I've got a mass hanging off one of the discs. As it falls, it causes the bar to go swinging around. The bar smacks into something, so we have a collision going on there. It smacks into it. It rolls along, goes down an inclined plane, hits something else, which then hits a spring, which oscillates back and forth. We have done all of the content for that kind. That was the third test for one of the years. Well, actually, more than one. But we've done everything except for the spring, as far as the Rube Goldberg goes. Now, I don't bring the Rube Goldberg test up to say, hey, that's going to be your final test. I bring it up because, one, I like the test, but it covers a great deal of what we are doing this semester, or in this last part, all in one test. It was also set up so that if I looked at your last answer and your last answer was right, then the rest of the test probably was right. What I did not take into account was the psychological impact of, since one part depended on the next part, through on the next part, some students got psyched out early. unfortunately. Still one of my favorite tests. All right. All right, there's one more conservation law we should cover. We have conservation of energy. Conservation of momentum. And I hand wave through that one, we derived this one. I'm gonna hand wave the next one, but the derivation is very similar to the middle one. So we have three major conservation laws involved here. The last one requires that we talk about angular momentum. First off, regular momentum, what is that equal to?
Mass times velocity.
If we transliterate, what's angular momentum equal to?
Inertia times. Or I times,
Would it be
omega, I don't know why.
All right. So if I wanted to know what the angular momentum of a disk is, that's, if I have a disk just sitting there, what's its angular momentum?
0.
Okay. So let's make it more interesting than that. So let's put a mass of 3 kilograms, the radius of 4 kilograms, and have this thing rotating around. Um, 6 radians per second. Disk. What's the angular momentum?
What was the moment of inertia for the disk again?
1/2 mr squared.
So 144.
The whole thing? Or just I?
The whole thing.
Units? joules per second, or joule seconds?
Joule seconds, or joules per second, I should say.
Let's see, that's not the way I was thinking about it, so let's see. Not joules per second, joule seconds actually works.
Say enough things when I get it right.
There's no nice one word unit for it. You could also do, well, you multiply kilogram meter squared times radians per second. So kilogram meter squared per second. And since a joule is a kilogram meter squared per second squared, joule seconds gets rid of one of the seconds. All right. Seems simple enough. Let's change it around just a little bit. Instead of a disc, make it a hoop. Rotating about that spot right there. Let's give it the same mass, and the same R, and the same angular velocity. What's the moment of inertia of a hoop?
MR squared?
Yep. So, what is the moment of, sorry, not that.